that's why I wrote it that way.
So this is the coefficient there, which is normalized to be 1.
Yeah, exactly.
Yeah, from the derivative.
Yeah, I mean, this represents the density gradient. I mean, this is B star over here, right? You weren't here on last week, but B star, we said, is rho s CS over L sub n, right? Right, so this L sub n, 1 over L sub n is equal to minus 1 over n dn dr. And this is n naught. So that's where that comes from, okay? You notice then here, in this sense, this and this is nothing but the total density in this model. This is the mean density and this is the fluctuation. Here we just write it explicitly as the total density, right? Because we don't, there's no Boltzmann approximation in the Hasegawa-Wakatani, okay? If it makes you feel better, you could replace this term with x over L sub n. It doesn't bother me, you know, in a slab model. And then you would have an exact correspondence with that, okay? You'll get to exactly the same equation when you're all said and done.
So QG is quite different to Hasegawa-Nima, but why people call it Charney Hasegawa-Nima?
Well, I mean, that's, look, Charney was one of the first, again, I looked into, just for fun, the history of the fluid literature once, okay? Charney was one of several people working on these ideas of a kind of a quasi 2D type equation for the 2D fluid. And it was, maybe somewhere late 50s or 60s. Okay, so he was one of the guys who was kind of the leader in the geophysical fluids world at that time, and he I think was one of the guys who was the first to derive that equation. But other people were in the act too, as you might guess, like Rossby or Rossby wave.
But my question, it seems that the dynamic is quite different. So why people call Charney?
Well, they're different and they're similar. I mean,
similar, yeah. But
I mean, the fundamental, I mean, depends what you mean by different. I mean, they clearly have a different behavior in the long wavelength limit. Right? In other words, the fact that this thing is here means in the limit of k per rho small, the behavior of this is very different than the behavior of k per rho small here. Okay? Put another way, in the limit of low k, the Rossby wave, as I was saying yesterday, is strongly dispersive. In the limit of low k, as we'll see, the drift wave is strongly non-dispersive. So there's a big difference in the low k limit. Yes, but the structure of the equation very similar.
okay.
It's a vorticity conservation equation. They both conserve a generalized energy and a generalized entropy. They both have the same kind of nonlinearity, similar structure. So I think there are more similarities than differences.
The nonlinearity are the same.
Yeah.
That is the
Really, the difference is in the linear response, and in particular, the long wavelength behavior of the linear response. All right, break. We're way over